Welcome! Step with me into the colorful world of textiles, a world where vibrant fabrics, intricate patterns, and soft textures surround us every day. But behind the beauty lies an often overlooked reality, the story of wastewater. Let us explore this journey, how textile wastewater is created, what it contains, how it affects our world, and the innovative ways we strive to clean it. The textile industry uses a wide range of chemicals in processes like sizing, scouring, bleaching, dyeing, and printing, leading to the discharge of wastewater containing various pollutants. Textile wastewater is a significant environmental problem generated from various textile manufacturing processes. It is characterized by high levels of pollutants, which can be harmful to aquatic life and human health. Beneath its colorful surface, textile wastewater is a mixture of extremes. Its pH can swing from acidic to highly alkaline. It is often warm to the touch and heavy with suspended particles and dissolved solids. Key characteristics include high BOD and COD, signaling organic and chemical pollution. Color, persistent and unyielding, often visible even at low concentrations. Salts, added during dyeing, which raise the total dissolved solids, TDS. Heavy metals like chromium and copper found in dyes and mordants. Toxic residues, some of which can harm aquatic life or accumulate in the food chain. Thankfully, this story doesn't end in disaster. Let's start the journey of clarifying murky textile wastewater with physicochemical treatment, the first line of defense. These methods work quietly but powerfully, removing visible pollution, balancing extremes, and neutralizing toxic elements. Wastewater first passes through rotating screens that remove large solids like lint and fabric scraps. It then flows into an equalization tank where it's gently stirred to maintain a steady flow and pollutant concentration, easing the load on later processes. Coagulants like alum are added to destabilize tiny suspended particles. Flocculants then bind these into larger clumps, flocks, that can settle out. This step removes many solids and some dyes, clarifying the water. Acids or alkalis are used to adjust the water's pH to a neutral range, 6.5 to 8.5, creating ideal conditions for the microorganisms in the next biological treatment stage. With pH balanced, solids removed, and a flow stabilized, the wastewater is now ready for the next stage of its transformation. Biological textile wastewater treatment refers to the use of microorganisms, primarily bacteria, to degrade organic pollutants in wastewater generated by textile industries. While textile wastewater often contains recalcitrant and colored compounds, biological treatment remains an essential part of the overall treatment process, particularly for BOD, COD, nitrogen, and some biodegradable dyes. Imagine a single tank performing multiple roles, receiving, treating, and clarifying textile wastewater in a precise rhythm. That's the elegance of the sequential batch reactor, or SBR, a time-based system that brings flexibility and efficiency to varying textile effluent loads. The cycle begins with the fill phase. Wastewater enters the tank and mixing begins, but without aeration. In this quiet stirring, denitrification starts, setting the stage for deeper treatment. Next comes the react phase. Air is introduced, and with it, life. Microorganisms awaken and get to work, breaking down BOD, COD, and ammonia. Some even tackle stubborn dyes, especially when trained to do so. Then the settle phase arrives. The air goes silent and everything slows. Microbes, now heavier with their work done, settle to the bottom as sludge. Above them, a clearer layer of treated water forms. In the decant phase, this clean water is gently drawn off the top, no sludge in sight if settling has gone well. Finally, the idle phase, a moment of pause, preparation, and removal. Excess sludge is wasted and the reactor is readied for the next performance. Disinfection is the final step in treated textile wastewater, especially important when the treated effluent is discharged into natural water bodies. Its purpose is to eliminate or inactivate pathogenic microorganisms, such as bacteria, viruses, and protozoa. Let's now explore the limitations of physicochemical and biological treatment methods in handling textile wastewater. Despite being effective for removing suspended solids, physicochemical treatment has drawbacks. Ineffective for dissolved organic pollutants and stable dyes. Produces large volumes of chemical sludge. Involves high chemical use and operational costs. Requires close pH monitoring. Fails to eliminate biological contaminants like pathogens. Though crucial for breaking down organic matter, biological treatment has its limits. Inefficient at removing color and dyes. Struggles with non-biodegradable or toxic compounds. Highly sensitive to pH, temperature, and sudden load changes. Demands long retention time and large space. Produces biological sludge needing further treatment. Hence, some advanced oxidation processes, like Fenton oxidation, is required for meeting discharge standards or enabling water reuse. The Fenton oxidation process for textile wastewater treatment involves a sequence of well-defined steps to ensure effective removal of dyes and organic pollutants. It begins with pre-treatment, where suspended solids are removed using filtration or sedimentation. This is followed by pH adjustment, bringing the wastewater into the acidic range of 2.5 to 4.0, which is essential for the Fenton reaction to proceed efficiently. Next, in the Fenton reaction stage, Fenton oxidation is based on the reaction of hydrogen peroxide, H2O2, with ferrous iron, Fe2+, under acidic conditions. This reaction produces highly reactive hydroxyl radicals, OH, which attack and degrade complex organic molecules, including dyes and surfactants. The core of the Fenton process is the generation of highly reactive hydroxyl radicals, OH, which have a strong oxidation potential, capable of breaking down complex organic molecules into simpler, less harmful compounds, or complete mineralization into CO2 and H2O. The ferric iron formed is then reduced back to ferrous iron by reacting with more hydrogen peroxide or other intermediates, sustaining the catalytic cycle. The final stage is post-treatment, where the acidic effluent is neutralized to a pH suitable for discharge or further processing. Iron precipitates, mainly in the form of ferric hydroxide, are removed as sludge through sedimentation. And that's how the Fenton process transforms complex textile wastewater into cleaner, safer effluent, one radical at a time. Thanks for watching.